And now we have come to the last lecture of Math 271 online for spring 2020. Thank you for sitting through these if you actually did. Conditional probability and Bayes' theorem. So we know how to calculate the probability of lots of things, but we understand how additional information changes our calculations of probabilities. So I'm going to imagine that the SEC bookstore surveyed 500 students. They asked what the major of each student is and what book this student is buying for their math class. And they get these results. These are all numbers that I made up. So if you're a business major, right, you buy Math 196 books because that's the business class. If you're a science major, you probably buy a calculus book. If you're undeclared, you probably buy Math 193 or a Math 196 book. Or science or calculus book, depending which class you're going to go in. So you can ask sort of questions of this data, right? And you see this data all the time in doing any kind of analysis. If a student selected at random, what's the probability that they're science major? Probability of science major, there's 75 students out of 500. So 75 out of 500. Probability that a student bought a Math 196 book and is a science major. Science major, Math 196 books, it was 10 out of 500, 2%. What's the probability that they bought a Math 196 book or is a science major? Remember that this is cases, right? So the probability of 196 or science would be out of 500 students. Being a science major, there's 75 science majors. 210 students bought Math 196 books, but the 75 includes this 10, the 210 includes this 10. We don't want to double count them, so we subtract that off. So 275 out of 500 either bought a Math 196 book or is a science major. So these are some fairly straightforward ones. Conditional cases are saying, given that a student bought a calculus book, what's the probability that they're a business major? So given that a student bought a calculus book, right, there's only 150 students. Out of that 150 students, how many of them were business majors? 10 out of 150. And we have a notation for that. Right? Probability that someone's a business major given that they're their calculus book. And it is a little reminiscent of being a fraction. This isn't actually a fraction. This is just a vertical divider. But 10 business students, 10 business majors out of 150 people who bought calculus books. Right? So 10 out of 150. And this is me telling you that we're not dealing with the entire 500 students. We're just dealing with the 150 who bought a calculus book. So given that a student is undeclared, what's the probability that the student bought a Math 193 book? Undeclared, we have 300 students who are undeclared. Of those 300, 100 of them bought a Math 196 book, Math 193 book. 110 bought a Math. 110 out of 300 of the undeclared students bought a Math 193 book. Oh my God, 110 out of 300. So probability that you bought a Math 193 book, given that you're undeclared, 110 out of 300, 300 undeclared students in the denominator. How many of those bought a 193 book? 110. So this is restricting the pool of respondents. Rather than dividing by 500, you divide it by 150 or 300. So the formula is this: probability of A given B equals probability of A intersection B divided by probability of B. So for problem 2, we'll just put it down here. So the formula, probability of A given B is probability of A and B over probability of B. So the probability that someone bought a calculus book, given that they're a business major, should be probability that they're a business major and bought a calculus book divided by the probability that they bought a calculus book. Right, that's the formula that we got. So that's what this should be. What's the probability that you're a business major and bought a calculus book? Well, that's 10 out of 500. That's the number we calculated here. What's the probability that you bought a calculus book? Calculus book, 150 out of 500. The 500s cancel out, and you get the 10 out of 150 that we thought we would get up there. So, probability being a business major, given that a calculus book, probability of being a business major and buying a calculus book out of all possible students divided by the probability of being a calculus. So, conditional probabilities show up in dealing with questions about replacement. And we have something called a probability tree, which is a useful thing to have seen at least. So suppose a box has 4 red marbles, 7 green marbles, and 3 white marbles. You draw 2 marbles from it in succession without replacement. So what's a probability tree? It's a tree like we've seen before. The root is where you start. The first set of vertices are the possible outcomes of the first draw. So we can get red, green, or white. And then the weights on the edges are the probability of that happening. We have 14 total marbles, 4 of those are red. So the probability of drawing a red marble is 4 out of 14. The probability of drawing a green marble is 7 out of 14. The probability of drawing a white marble is 3 out of 14. So I'm building up a weighted tree where the weights on the edges are the probabilities of an event happening. Now, the second marble can be red, green, or white. But what's the probability of getting a red marble on the second draw? Well, we took 1 marble out and put it aside. So there's only 13 marbles left in there. How many, if I picked 1 red out, how many red are left? Well, 3. What's the probability of getting a green marble once I've taken out 1 red marble? Well, that's going to be 7 out of 13, and then getting a white marble would be 3 out of 13. So note that the probability of getting a red marble has changed because once I've drawn a red marble out, it's gone from 4 out of 14 to 3 out of 13. Probability of getting a green marble has also changed. So this is a condition, right? If you pull out 1 red marble, you've changed the probabilities a little bit. So same thing with the green marble. You could get red, green, or white. What's the probability of getting a red marble after you draw a green marble? That would be 4 out of 13, 6 out of 13 for getting a green marble, and 3 out of 13 for getting a white marble. And then 1, 2, 3, red, green, and white. And 4 out of 13, 7 out of 13, but only 2 out of 13 for the white. So if we're thinking about drawing 2 marbles, there's 9 possible outcomes. You can do red and red, red and green, red and white, green and red, green and green, green and white, white and red, white and green, white and white. So there's 9 possible outcomes because there's 9 different sequences that you can pull things at. So probability of red, then white means what's the probability of going out this branch? And what do you do if you do a sequence of things? You multiply the probabilities together, right? Multiplication sequence. So 4 out of 14 times 3 out of 13. Ending up with a red marble and a white marble, that means either this case or this case. So 4 out of 14 times 3 out of 13, that's this probability, plus this probability, which is 3 out of 14 times 4 out of 13. They're actually the same thing, so the numbers get shifted around a little bit. What's the probability of not getting a white marble? Well, you could do red and then red, red and then green, plus green and then red, plus green and green. Right, so the probability of not getting a white marble means you did red and then red, or you did red and green, or you did green and red, or you did green and green. So not white can be divided up into these four cases. Red and then red is 4 out of 14 times 3 out of 13. Red and then green is 4 out of 14 times 7 out of 13. Green and then red is 7 out of 14 times 4 out of 13 plus green and then green is 7 out of 14 times 6 out of 13. That gives you your probabilities. And I think I actually did calculate that at some point. This is a 0.6044. So 60.44% chance of not getting a white marble. What's the probability of getting at least one white marble, either one or two? Well, if the probability of getting no white marbles is 60.44%, the probability of getting at least one white marble is 100 minus that, which is 39.56%. There's our complements again, right? Remember, complements are really powerful tools. Okay. Now, in dealing with conditional probabilities, you have to be careful about which probabilities are conditional, which are not. So there's a call center, it's got this data. The names of the people making the calls, Dale, Rusty, and Lee. The first one is the percentage of all calls each one makes. So Dale makes 40% of all calls, Rusty 25%, Lee 35%. The second one is the percentage of each person's calls that are hangups. So 20% of Dale's calls are hangups. This is not saying 20% of all calls are hangups, just 20% of the time that Dale makes the call, there's a hangup. Rusty kind of sucks at this job. 55% of the time he gets a hangup. Lee is not as bad as Rusty, but not as good as Dale. 30% of the time Lee gets a hangup. So probability of D, what's the probability that Dale made the call? What's the probability of having a hangup? What's the probability of not having a hangup? What's the probability that Dale made a call that ended up in a hangup? What's the probability that a hangup happened, that Dale made the call given that a hangup happened? So there are a couple different ways to deal with this. I'm going to assume 10,000 calls are made. And then I'm going to try and figure out what goes where. So 10,000 calls are made. Dale makes 40% of them, so he makes 4,000 calls. Rusty, 2,500. Lee, 3,500. Or she, I don't know the gender of any of these people. So 20% of all of Dale's calls are hangups. So 800, 20% of 4,000 is 800 hangups for Dale, which means that 3,200 calls were not hung up on. Rusty, 55% of Rusty's 2,500 calls are hangups. So that's 1,375. And how many are not hangups? 1,125. For Lee, 30% of Lee's 3,500 calls are hangups. So that's 1,050. And 2,450 are not. So the totals, out of every 10,000 calls, about a third are hangups and 2/3 are not, roughly. So now I have all these totals. And so now I can make some statements. What's the probability that Dale made the call? Well, 4,000 out of 10,000. Dale made 4,000 calls out of 10,000, which is 0.4, which is, we already knew that. He made 40% of the calls. What's the probability of getting a hangup? Well, 3,225 out of 10,000. Right. And what is that? Oh, that's actually easy to do. 0.3225%. So 32.25%. Notice it's a little bit easier to get that number than to get it from here. What's the probability of not getting a hangup? Not getting a hangup is 6,775 out of 10,000, which is 0.6775. That's not surprising. What's the probability of PH given D? Probability of a hangup given that Dale made the call. So This is asking what percentage of Dale's calls were hangups. And so Dale made 4,000 calls, 800 of them are hangups, and that's 0.20. And we knew that, so that's not any new data. But what's the probability D given H? Probability that Dale made the call given that it's a hangup. Dale made 800 calls that are hangups. There were 3225 hangup calls, and that's 0.2481. So Dale's responsible for about a quarter of all the hangups. So notice that's actually higher than his percentage, right? Because Rusty got a lot of hangups, right? But Rusty doesn't make a whole lot of calls, right? Dale makes a whole lot of calls, gets very few hangups, but you know the numbers are a little bit closer than you'd think. Okay, so this is a useful way to do these sorts of things. How do you do? So to get the probability of the hangups, we took this number and we divided by 10,000. That gave me this. How do you get that from this original table? Right? And this 3225 is the 800 hangups that Dale got. Where did the 800 come from? Well, that's 0.2 times the 4,000. So it's 0.2 times 0.4. So the probability of a hangup is the probability that you got a hangup given that Dale made the call, plus the probability that you got a hangup given that Rusty made the call, plus the probability that you hang up that Lee got the call. But what's the probability that you got a hangup given that Dale got the call? That's the probability that Dale made the call times the probability that, oh, sorry, got it backwards. Probability of a hangup is a probability that you got a hangup and Dale made the call, plus the probability that you got a hangup and Rusty got the call, plus the probability that you got a hangup and Lee made the call. But the probability that you got a hangup and that Dale made the call is the probability that Dale made the call times the probability that Dale made the call that there was a hangup given that Dale made the call. So the probability that there was a hangup that from Rusty, right? That's the probability that Rusty made the call times the probability that Rusty got hung up on. So probability that Rusty made the call times the probability that there was a hangup given that Rusty made the call, plus the probability that Lee made the call times the probability that there was a hangup given that Lee made the call. So what's the probability that Dale made the call? 0.40. What's the probability that he was hung up on? 0.20 plus 55% of calls are made by Rusty and he was hung up on 25 25% of calls were made by Rusty and he was hung up on 55% of the time, and Lee made 35% of all calls and he was hung up on, or she was hung up on 30% of the time. So I can take these numbers, multiply them together, and that should give me my 0.32225. Okay, so this number, probability that there was a hang up given that Dale made the call, that's just this number straight up, 20%. Probability that Dale made the call given that there was a hang up, well, that's this. So probability that Dale made the call given that there was hang up, how do you get that from the original data? Well, probability that Dale made the call and there was a hang up over the probability of there being a hang up. But this is the probability that there was a hang up given that Dale made the call times the probability of Dale making the call. That's the definition of conditional probability divided by the probability of H. The probability of H is given here. I'm not even sure I want to write that down again, but I guess I will. H given D plus probability of, let's see, Rusty, probability of Rusty, hang up given Rusty, plus probability of Lee making the call times probability that there's a hang up given that Lee makes the call. So what's the probability, given that there's a hang up, what's the probability that Dale made the call? Well, there's probability that Dale made the call and there's a hang up divided by the probability of a hang up. Dale making car and there's a hang up. That's this. These numbers we know from the table. These numbers we all know from the table. This is called Bayes' theorem. It's a way to get this condition from that condition. The notation is just grim. I like to deal with Bayes' theorem by doing this sort of thing. It just makes everything a lot clearer about what I want to do. Okay, and that's it.